So I think, I mean, I already like partially presented the next speaker, but basically next speaker will be uh, um, Sean Phillips with his talk. I mean, I would say it's gonna be, um, maybe this talk will rip your head off at, especially at the ends of the day. But I mean, who knows? I mean, people like kind of tough stuff. So so the talk is on explainable AI analysis and visualization applications from brain computer interfaces to ChatGPT. So again, please welcome Sean Phillips back on the stage.
Hey, all right.
Did you
All right,
like
I'm
the
good. All
introduction,
right.
Sean? I mean, that's from my like experience, like watching your talks. So that was quite kind of mind blowing. So it was like, too much for me. So, but yeah, but this is good stuff.
Yeah, thank you. I need to share my screen here, and
Sure,
right now it
go
says that
for it.
okay. Oh, okay. It's
I
enabled now.
think
Okay.
yeah.
Screen number one. Share. Okay. We'll move this off so people aren't confused, and pull open some slides. Okay. So this presentation actually is two halves. The first half is about focused on a use case centered around brain-computer interfaces. And when I say brain-computer interfaces, I mean actually the interface is used to receive signals directly from the neurons or different areas of the brain, and then analyze the results of those. And I'll explain those when we get there. The second half, and this ties back to the previous conversation, actually, is we're doing a lot of work with generative AI and large language models, and one of the many things that we're investigating in a sort of deep technical manner is, given a generative AI thing like a large language model like ChatGPT, what is possible to be able to try to detect that such a thing is generated by a large language model. And the results are positive but mixed, and there's a lot of caveats, but we've made some progress, and we're going to share that. And this will be the first time it's ever been shared in public, this particular effort. Okay, so before we go any further, let me say that I work for the Johns Hopkins University Applied Physics Lab, and we are a university affiliated nonprofit research center. We service the U.S. government directly. And so at no point here are we trying to sell anything. This is not a product placement. This is not us looking for cash. We've got all the work we need. We just want to share this work with the people of the world. You will see a lot of this demonstration through a tool that we call Trinity. Trinity is open source. It is a JavaFX visualization that does hyperdimensional vector visualization and analysis on hyperdimensional data sets. Things like deep learning models, large language models, and we'll get to that. But where did Trinity come from, and why do we even call it Trinity, right? A few years ago, I was supporting a brain-computer interface project. There's a picture of it right there. That guy has a literal set of plugs into its surgically implanted in its this is a picture of the participant who has this surgically implanted interface directly in his head, and he's manipulating a JavaFX visualization in kind of like a fake cyber defense scenario. And the project was called Neurally Enhanced Operator, NEO, and that's cool, right? This guy's literally controlling the computer and doing abstract things with his brain. But there was a problem. You see, in order to decode what was coming off of the guy's neurons each day for the experiments they were running, they had to retrain their model each morning, and that required tons and tons of repetitions. If they didn't, the decoding model would just simply fail or become highly unreliable. So I remember, I was the Viz guy, but I remember watching this, and it would take like an hour and a half each day. And so if you've got the only person in the world with this surgically implanted device, and it's taking an hour and a half to, retrain your models to decode your stuff before you can even begin to do experiments, that's a lot of wasted effort. So we did some research, and we realized what was happening was that the states that we were training the model for, i.e., the neural states that this person was in each morning, were just simply different each day. And so if you look at, so we created a visual to prove this. If you look at this visualization, this is a JavaVex tool. This is an early precursor version of Trinity. What you see are two waveforms, some red trajectories and some blue. And what those represent are two different types of acts. Red is a neural gesture where he's at rest. He's intentionally doing nothing. And then the blue trajectories represent a specific abstract neural gesture that we're asking him to do as part of the experiment. And if you notice, there are multiple loops there. They all look and feel the same. They're just all kind of sort of off. All right. This is a lot like how a deep learning model might do image recognition. It's trained on different orientations, different angles of an image, but essentially it's a lot of different versions of the same type of image. Like you want to detect a dog in different poses, right? And so the reason this guy's model had to be retrained was because his brain was a little bit different each day. Maybe he had some coffee, maybe he did it, maybe he was in a bad mood. And that was really the problem. So we made this tool, and we call it Trinity because, Neo, Trinity, Matrix, these things go together, right? So later, this was not the only brain-computer interface project. We had some other internal research and development doing using different technologies, different hardware to attempt to enable brain-computer interfaces for applications. And the next one, when they came to me and said, "Hey, can you expand Trinity to handle this other use case?" I did, but before and I'm going to show you that data and what it looks and feels like, and why this analysis approach works, and then I'm going to show why this analysis method extends naturally to deep learning models, especially large language models. But first, let me explain what you're about to see. There's in the brain-computer interface world, there's a concept of semantics. What does something mean to you? And actually, this is really very similar to how artificial neural networks, i.e., deep learning models, are modeled, because they are modeled against biological neural networks, i.e., the brain. So there's a concept of exogenous semantics. What does that really mean? All that means is that you as a human, you see something, you see things about it, you experience it, and aspects of that go into your internal lexicon, your internal dictionary, if you will, right? That's how you learn. Then later, you are then put in situations where you need to make a decision. Let's say, what am I looking at right now? What do I expect to see right here, right now? That's an endogenous semantic, as in something you're perceiving, something you see based on your experience from before. This is why when we see this essentially, in a really, really, really lightweight, high level way, explains why when we hit a scenario for the first time, like you're put into a situation you've never been in before, sometimes we don't do well. We are creative, we're higher level thinking beings, but the reality is we have not been in this situation before, and so we're kind of doing our best. And isn't that just like a deep learning model? That's exactly what a deep learning model has to do. And that's why neural networks were not effective for anything beyond trivial problems until we started building out these deep learning architectures, which of course require just vast amounts of information to train on. What we're basically doing is putting ourselves, i.e., our models, in every single possible situation we can conceive of. So in this particular experiment, they have some hardware. These guys are the researchers, and they were testing out themselves. What this is what they call a non-invasive BCI, meaning they didn't have to drill anything into their head. There were no surgical implants. These things are very tightly wrapped around their head, and then signals from the brain are scanned by a series of receptors. And there's I forget the number of combinations, something like 418 receptors, that sort of thing. And what that does is it creates a vector, and then the model has to decode that vector. Okay, this is very similar to any deep learning model that you might leverage, like a large language model. Like, for example, ChatGPT, when it associates a set of text in vector space, hyperdimensional vector space, it has a 1,536 dimension wide vector. Okay, same type of problem. So for the experiments that they were running, and then we'll get to a live demo after this, what they did was they put these caps on the participants, and then they had them stare at a computer, and then they would flash these stencil images. Not for not very long, just long enough where the human has plenty of time to recognize that the image is on the screen, and then to think about it for a second. Then they mask off the screen so that it kind of eliminates that sort of view. And then they are asked for several seconds to think about what that image means to them. Is it a building? Is it a vehicle? Is it edible? Is it a creature? Things like that. And then they stopped, and then they rested for a second, and then they redid it again. And they did this for about 15 minutes straight with 100, well, over almost 1,000 images. I forget the exact number. And so what you're going to see is the vector analysis over time of how this data was interpreted by one of our participants. So I'm going to switch to Trinity, which is the tool. And I'm going to do everything live. I guess I'm a glutton for punishment. Okay. So let's see here. I'm going to go and load one of these data files. Okay. So, and unfortunately, because it's being shared over Zoom, and this is a 3D application, there's going to be some frame rate reduction. There are videos online if you want to see this in its full 60 frames per second glory. But essentially, these are all the data points in time as projected from the 418 dimension wide vector space that's coming off the brain into a decoded lower dimensional 12 dimensional semantic space. So you can see, for example, right now we're looking at the axes as is it a body part? Is it a building? Is it an animal? And there are multiple dimensions. So I'm going to just shift through the dimensions, and you can see I'm just hitting a button on the keyboard, and I'm choosing which dimensions I want to look at this moment. But here's the problem. It's all just kind of like a mass, right? Because this is all the data in time. And it's color-coded, like by type. So like, for example, I'm just going to click on these red ones here. And at that moment in time, it was a chimney. So you would expect that it's probably going to be somewhere closer to the building end of the scale, and probably farther away from the body part scale, right? But how do we look at what the user was thinking at that moment? Well, that's where we use this playhead tool right here. Okay, let's enable the trajectory actually. Okay, so I'm going to enable a temporal order trajectory. And we're going to get started, and we're going to hit play. And maybe speed it up a little bit because I don't have a lot of time here. So you can see over time, this is how the person is thinking in terms of these semantics. Oh, let's slow it down a little bit. So right here, at this moment in time, that this image of a screwdriver was up on the screen. And you can see, it's the trajectory is moving away from, is it an animal? Because that doesn't really make sense. But it also really doesn't make sense that it's a building or a body part. So let's see. The next event coming up is chair. So let's get over to chair. And I'm just guessing, by the way. I didn't plan this particular bit here. So for whatever reason, the person thinking about this doesn't see this as a body part or an animal. But notice how this is starting to move back towards the center. and back towards, is it a building? Because, and that kind of makes sense, right? Like a chair is a man-made object. It's an object. It's not a building, but buildings are man-made. This is a man-made thing. So this is the human brain semantically interpreting this particular image. It's just an example, and there's more. And I could keep playing this if you really, really want to see it, right? And there's so much more that could be said on this. This is not all that different than what you get from these generative AI models. It's sort of like the hallucination part. Like they call it hallucination in large language models because, it's, I think I really wish they hadn't picked that term because it kind of sabotages people's trust in these types of things. But essentially what it's trying to, the definition of, I'm not going to give you a definition of hallucination, but it's how is it deviating from a truth that it was trained on, so to speak, truth, right? With this chair, in this context, it's deviating from building. So it's not like a perfect fit. And if we keep playing, we could look at different items here and we could get through them all and you would see what I mean. But again, this is difficult to work with because you've got this mass of data here. Okay. So what we started doing was building in tools that would normally be utilized for deep learning model and AI model analysis, like dimension reduction and clustering techniques. And we said, I wonder if we can apply this here. So here is Trinity has as an alternative view, a projections view. What does that mean? In this sort of context, a projection is anytime you take the high dimensional data, the hyperdimensional data. So in the case of a large language model, the vector embeddings. In this case, it's the data vectors coming off of the neural hardware. And then you can run a dimension reduction type tool. And for example, we've got UMAP built into Trinity, and then that'll generate clusters, which are actually kind of useful. So I wrote some settings down because I've done a lot of testing over the years. And one of the problems when you do these sort of dimension reductions, and in this case, I'm using UMAP, which is published in 2018, I want to say, and it stands for Uniform Manifold Approximation Projection. I'm pretty sure I got that right. The point is, it's a nonlinear dimension reduction technique, originally used for visualization, but there's other utilities for it. And what it's doing is essentially a really jacked up K nearest neighbors type approximation, does a bunch of pairwise distance checks between all the different data points, and then it spreads out and clusters the resulting lower dimensional projection points based on differences, that sort of thing. And that's really cool. But the problem with these types of tools is there's a lot of settings, and different settings can give you wildly different projections. And you can kind of treat each projection like a shadow of the truth. If the sun is directly behind you, the shadow that it projects of you is true at that exact setting, at that exact angle. And if you were to change your body a little bit, or the sun moves a little bit, that shadow changes, but it's also true. It's no less true. That is the type of problem that we try to solve here. And I'm going to go into more detail here with my next example that is based on ChatGPT. But let me finish this brain-computer interface example by demonstrating using UMAP on this data. Now, in this case, let's see here. I'm going to, I have some very specific settings. So I could spend probably half a day just going through like how to use UMAP and what the differences are. But essentially what I'm going to be asking UMAP to do is look at the data from a very localized view. Like, try to maintain as much of the local structure as you can without sacrificing too much of the global information. And because I've done this a million times, I know what's about to happen here. So I'm going to start off by just running UMAP with a Euclidean distance metric. Euclidean just means straight line distance. And I'm pulling this from the hyperdimensional state. And as you can see, that's really interesting because what we've got here is this like sort of like roller coaster track, colorized in the order that they occurred. So if I go over here and I just click on one of these here, no event. Okay, let's click a different color. Okay, celery. At that moment, this was the phase in the experiment where celery was being shown. So that's really interesting because now what we have is effectively a time ordered track of our experiment session. And if we play around with the settings, and there's just the combinatorial space is huge. It's not worth going into, but just even changing the distance metric alone, and maybe I don't know. Yeah, I mean, I won't even touch the other settings. And if we run this again, it's going to recalculate this projection. Oh, good. I do not want to install that now. And it's a little bit different. See, a little bit fuzzier. Let's see here. Let's zoom in here real quick. It's a slightly different track, but it's still useful. And let's see if we. This is the lead track. So if we hit play, as you can see, let's slow it down a little bit. Zoom in. You can see that it's following along as it occurs. So this is interesting because now we have a method, a practical method, to sort of know exactly what phase we're in the session without having any knowledge necessarily at this moment of what the time is, we now have a method for figuring out where we are in our temporal order, just simply by doing a dimension reduction and clustering effort on the high dimensional data. And that's pretty useful. Okay. So let's change gears a little bit. I'm going to go back to my slides. Okay. Okay, still got some time. That's good. This is where we begin to tie back into the conversation that we just had in the panel of experts, and this is about how would one go about using this sort of vector analysis tech methods, these numerical methods oriented towards high dimensional vectors. How would you use that potentially to detect whether or not a generated bit of content is actually generated versus human? But it's not that simple. What is the actual problem here? Because nobody's actually really angry that we can generate content. I mean, that's pretty cool, right? The problem is how they're using it. There's a lot of bad actors out there, and every time technology is created, it of course the first people to almost inevitably the first people to use it en masse are people with bad intentions because they the good guys, they stop to think about the ramifications first, right? And so what are the bad actors doing? They're using things like ChatGPT and other large language models to generate and spread fake news, misinformation, propaganda. But now they're able to do it at a massive precision targeting scale. And so this allows them to not only generate said things, but then they can generate for very, very small, slim, targeted online communities. So what we're trying to do is identify methods that would potentially detect that. Now, we started to have a debate. We ran out of time in the last session about whether or not it's even possible to detect something like this. And let me be the first to say it is not possible to detect generated content 100% of the time. It is also not possible to generate content, to detect generated content if the content itself is small enough. What do I mean by this? It's an information problem. How much information do you have? If somebody uses ChatGPT to generate 3 or 4 words, there's no information there. There's nothing there to work with. That those could have been picked on a Ouija board. It's almost irrelevant. And if somebody uses ChatGPT to generate like an 18-page essay or report, if they don't alter anything in it, it's actually kind of pretty easy to detect, because there's the more content that is generating, the more likely there's going to be some sort of obvious thing that even a human could just look at and say, yeah, that's not right. That looks like it's written by a 5-year-old. Where it gets interesting, and where these bad actors are utilizing these tools, are for the sort of small to medium sized blurbs of text, the social media sized chunks of text. A Twitter post, a Reddit response, a series of Reddit responses, et cetera, et cetera. Pick your favorite social media. They're all garbage, but but the point is, a lot of people are using it, right? So if a solution is going to be useful for detection, then it needs to be able to work or show some utility on that sort of paragraph social media size blurb. But there's other things that we really need. What we really need is something that can be deployed practically. Okay, something that doesn't require a supercomputer, something that is easy to use and automate. Right, because it's pretty darn easy to use these very extensive large language models now. Right, we got to keep up. We also need the solutions to scale with these large language models. What do I mean by that? They're getting ready to release DALL-E 3, right? I thought they just released DALL-E 2, right? These things are going to get bigger and bigger, and the hardware is going to the innovation in the hardware world is going to keep happening to try to keep up with this. So you can't provide solutions which just kind of are looking for inconsistencies, because as these tools get better and better, they're going to become more and more precise with the text they're generating. And so those sort of topical, well, I'm only going to look at the text itself. I'm going to look at word count. I'm going to look at similarity of text by itself. That's not going to work. And to make matters worse, every time that the good guys come up with a way to detect something using those types of techniques, i.e., is this a deep fake? Is this a deep fake image? Is this a deep fake audio clip? The bad guys then use that research to make their tools better. It's an arms race, and whenever it comes to an arms race, the bad guys always win. Remember that. You got to short circuit the arms race. So we need something that scales, and it's got to scale numerically. And then finally, and this was something I was trying to talk about in the last session. The solution must offer an asymmetric cost. It can't cost us more to use our detection methods than it does for the adversaries to use their spreading their propaganda mechanisms, because then they win, right? They're going to keep using it, and they're going to wear us all down. But at the same time, it can't be a one-to-one. If it's one-to-one, they still are incentivized to utilize it. What we need to do is come up with solutions that they're not guaranteed, because you can't guarantee detection, but it makes it so that in order for them to be successful with spreading the propaganda, they have to spend much more resources, money, time, effort. At that point, it becomes something that they don't want to do. They'll try to do other things. It's not worth their time. And that's really the ultimate goal here. So there are multiple ways to do it. So how could we maybe do it? And this is where, if you haven't paid attention up until now, this is where I want you to start paying attention, because this method, although I'm applying it to the sort of detection use case, this is a method that could be used because of its numeric neutrality on a whole number of use cases, both positive and negative. The approach is one of masking, okay? And masking and then permutations. So let's say we get a chunk of text, and we do not know ahead of time that chunk of text is generated by a human or ChatGPT, let's say. And somebody says, please, what's the likelihood that was generated by ChatGPT? So one method that we're going to demonstrate here, and it shows some promise, is this masked permutations thing. So essentially, what you're doing is you're going to make a bunch of variations of that text, and you're going to get the vector embedding the embedding vectors from a targeted model, and then do similarity analysis on those. What do I mean by that? Well, let's say you get this input prompt, and we're not testing the prompt, right? We're just saying, hey, this text was generated, and it's blah, 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 right? An example of a masked permutation would be any one of these, where you're essentially saying, hey, remove this word, every other word, randomly remove words. Maybe you have a better algorithm for selecting those words. And I'll get, if we have time, I want to talk about stuff like that at the end here because those things matter. But basically, you're going to generate a bunch of permutations. And then, of course, you ask ChatGPT, please fill in the blanks. So basically, ChatGPT is acting, it's doing like a Mad Lib if anybody's remembers those, like fill in the blanks, that sort of thing. But here's the catch. You know that all those masked permutations, those variants, for a fact, 100% that those were generated by ChatGPT. So then, if you know that, then now you can test a hypothesis, which is if the original text was human generated, it should be closer to that. It should be closer to a human generated version than or variants than it would be to the ChatGPT variants. What you're basically doing is generating a point cloud and then doing a probability distribution against that point cloud. Once you have, okay, what does that look like? I'm going to show you in Trinity. We're going to pull in some ChatGPT generated permutations and some human generated permutations. And we're going to colorize them, that sort of thing. We're going to show how they look in the hyperdimensional space, and here's a preview, but it's a little globbish, there's the decision boundaries are all woven together, and it's not all that useful. But then we're going to use that projection tool that I just showed you with the brain computer interface data. We're going to start using that tool, but with this text information. And we're going to see that you can get some great separation potentially, and you can use different distance metrics to get different configurations. Now it's starting to, and then you can recolor them based on their original source, and it starts to show the separation. And then finally, we're going to start looking at 3D volumes, i.e. the approximated manifolds, a big fancy word to say like 3D shape. And we're going to look at distances from those manifolds, and we can start to see a practical method that has potential to scale well with these models for doing a likelihood detection. So without further ado, we'll switch back to Trinity. And we'll go back over to our hyperspace view. Okay. And we will, instead of looking at BCI data, we will look at some ChatGPT data, right? So we're going to first drag our ChatGPT generated data. Do I want to clear the data? Yeah, sure, because we don't want to mix our brain-computer interface data with ChatGPT data. Doesn't make sense. So that's crunching for a couple seconds. There's a lot of text there. It's getting everything into memory, that sort of thing. Okay, great. Hurry up now. Yeah, right? There it is. It's giving me a hard time, and I don't know why. Something happens very slow. All right. I'll start it back up again. I don't know what happened there. It's funny. You make these tools, right? And they you run through it like 18,000 times to make sure that there's no problems. And then right during the demo, it doesn't work because maybe you're connected to Zoom or something like that. I'm rerunning it now. Okay, great. Run it. Drag this back in. There's no data there. Just go ahead and do it. I don't know. Something's up. some combination of being connected to Zoom and Devoxx. It does not like this. All right, it got through. Lucky me. Thought I was gonna have to like wing it. Okay, so that was a little scary, but so here what we have is exactly what I pointed out before in the slides, and as you can see, that's a little globby, that sort of thing, right? But there is some separation to a certain extent. Like if I go over here, I'm just going to click on any one of these. Here's the chat. Here, this turns out to be a ChatGPT. Well, they're all ChatGPT generated. And here's a permutation. Here's the actual text that was produced right here. And if we go in there, get way down in there, we can see. Oh, well, okay. What's this one? Ah, that's the original. So you can see this is a point cloud associated with it. And we can take a look at that exact one right there. Zoom out. So this text, yeah. This right here, this text is a variation of this particular text, okay? And so if we were to repeat this for human-generated variations, you would think that what we would be able to see is where they separate. But what we find in the hyperdimensional space is that I'm about to drag in the human one. Let's see if this actually works, because, man, it gave me a hard time last time. I do not want to clear the data. I want to see it in the same exact space. It'll get there eventually. As it's loading, I'll try to fill in time. What we're going to find is that in the hyperdimensional space, the data does not separate well. What do I mean by separation? I mean that it's not clear in high dimensional space where one type of data starts and ends and another begins. So why might that be? Well, part of the problem is we don't live in a hyperdimensional world. We live in a three-dimensional world, and we're trying to render these things in 3 dimensions, and that's really, and there's tricks to show more dimensions than 3, so to speak. And no, I do not want to clear the queue. And there we go, it's loaded. So what we can see here is, like what I was just saying, there's almost no separation. Like, how do you know where human versus ChatGPT is? So, okay, let's use that dimension reduction thing that I showed you earlier with the brain computer interface stuff, okay? It's generically applicable. So if we bring this up, and I won't go through explaining UMAP again. You already saw it, right? This time, though, what I'm going to do is punch in some numbers here that I've been prepared, right? And my goal here is to get a configuration of UMAP. I'm going to lower increase the minimum distance so it factors in more of the structure. Increase how much it mixes everything together, and increase how much we spread this thing around. And this time we're going to use a simple Euclidean distance measurement, and we're going to touch this baby off, okay? Okay. Well. Okay. We start to see all these clouds here, right? Let's get rid of the sidewalls here. Okay. Shadow cube. Okay. Good there. And let's get rid of the 2D projections on the side. Now we're just looking at the 3D dimension reduced data, okay? And as you can start to see here, let me reduce the point size so it's a little cleaner. I'm just gonna pick one of these. It really doesn't matter. Oof, that explains why. Ooh, I ran out. I ran out of memory. Oh, Zoom is killing me here. Oh man, that's great. So let's see. Do I even have time to keep plunging through? I don't know. So the I'll rather than I'll spare you going through that whole thing again. I'll point at what you can see. The clearly each one of these clouds represents a different point group, right? And there are some, you can look, if you look closely, you can see that there are some ones that are mixed together, and there's some that are more uniform. You see some sort of insiders here, and so this gets back to one of the things we're talking about, which is it's not possible to be 100% certain that a piece of text belongs to a group, i.e., a projection, i.e., ChatGPT generated versus human generated. Okay, but what is possible is to get within a certain threshold. Okay, and the, you know, it's kind of like a numbers game, right? If you're looking for, in this case, we did 50 permutations for each input text. If you look at a group of 50, let's say, right, and most of them are all pretty close together, but you get a couple ones that are for whatever reason shouldn't be in this group, but they are. Those are outliers, if you will. That's a win. If your objective is to make it easier to potentially detect these sort of ChatGPT generated bits of text, because when we're talking about internet scale type media, we're not talking like a dozen, twos, threes. We're talking thousands, tens of thousands, hundreds of thousands, like, right? And how is it being done right now? You've got human analysts who are being forced to look at text. The resources just aren't there. So it does absolutely become a numbers game. So a method like this would allow us to actually automate it. Now, I'm not saying we automate the 3D display. The 3D display was necessary to vet the approach. I'm going to switch back to my slides, because the slides have some interesting stuff. All I'm doing here is showing the results, right? But then all the math under the hood is effectively, it could be scripted. It could be run massively in parallel using Java services. And so that, I think that's actually the goal that we're driving for with regards to research like this. And with my last few minutes here, where does it get really interesting? Like, okay, so you separated some clouds, you kind of group things together. There's a few outliers here or there, but and this is what I wanted to show you before I completely ran out of memory here, which is once you have a configuration for a dimension reduction and clustering type of capability, well, and let's assume UMAP for now, but there's others, and they have different utilities for different problems. Once you have that clustering, if you were to lock that setting and essentially freeze what they call the transformation matrix of that clustering algorithm, the transformation matrix is effectively the coordinate transformation that is learned from the data by the algorithm. What you end up with is a sort of fixed transform, a hypermap, to take inputs from the hyperdimensional space and push them to a common lower dimensional approximation. Okay, big words, but essentially you're mapping the complex data down to the same simple lower space data. If you find a configuration that is suitable for your use case, you freeze that and then reuse that to project all new data coming in. Well, now suddenly it becomes a very simple three-dimensional polyhedra problem. As in, like in this slide, you've got, okay, here is a decision manifold. It is of this particular label. And if I want to test this point against this decision manifold, now all I'm doing is doing very practical, very straightforward Euclidean distance checks. Meaning, how far away is this point from this cluster? Is it inside the cluster? Like if you look closely here, you see this little yellow dot here. That's the original text. for this particular manifold, manifold grouping. These are all the permutations for that manifold. Like, is it inside the cluster? Is it closer to the original than any of the outside points? Is it on the boundary? Boundary being defined as like a convex hull. Is it outside the hull but far away? Well, if it's far away from the hull, then it's pretty safe to assume that it has nothing to do with those permutations, and therefore it's very dissimilar, so to speak, from that original text. But if it's very close, within some sort of threshold, well, it's not proving that it is related to that text. It's not proving the similarity, but what it is doing is giving us a very practical method for an indicator, a red flag. Get human eyes on this bit right here, because this is too similar based on our distance checks to these other things that we're really worried about. And that's really all this is. Now, is this a solution? As it stands, not yet. This is the start of a method that seems practical, that scales well with precision, that has potential going forward. Will it survive the next generation of large language models? Possibly. We think so. We don't know for certain. And only time will tell. More testing, more test evaluation. Does this work for all scenarios? We don't know. We just did this research over the summer, and so it's not actually guaranteed that it's going to work in a broad way, but it certainly seems to show that promise in this sort of like very, very specific application. And I might add that Trinity, the software tool, and frankly, this method, it doesn't know ChatGPT from a hole in the ground. Like, it doesn't know or care. All that the software cares about, and all that the method cares about, are vectors. Give it the vectors, crunch the numbers, measure the distances. Right. So, in other words, we believe strongly that a very important secondary benefit of this research is simply that this is a very generic, practical approach that could be applied to other use cases beyond just detection. It could be you're trying to keep an eye on the discourse happening in a very, very politically a politically tense situation, and you're saying, well, it seems like the way people are talking, they're not just angry, they're specifically talking about this problem over here because it's very similar to this thing that we're worried about. You could do something like that. Now, that's kind of a surveillance problem, and now it's kind of like, well, is that good or bad? It depends on how just like any use of AI, it depends on how you use it. But you can use your imagination. The way forward, I guess, in conclusion, because I'm almost out of time, I think, the way forward for working with these sorts of massive deep learning models, these massive generative models, the ways forward, they can't operate on the output. The output's almost a secondary thing. They must operate on the vectors themselves. You must treat, going forward, vectors as the first class citizen of any of your paradigms. Okay? And this is what I've shown you today is just one sort of method for doing that. And I'm sorry about the technical difficulties with using the software. It looks like that I just, with the combination of Zoom and Vimix and this 3D Viz thing running, my GPU just said, no, I can't do it anymore. So, okay, sorry about that. But if anybody's interested, this is open source software. You can get it from, let's see, GitHub. And it is here. You will know that you're in the right spot because it's got this really cool 80s style retro wave theme going on. And we're always happy, just because a couple APL people are leading the way in terms of development, we absolutely would be interested in supporting other folks for things in terms of like the open source model. And so we're always welcoming pull requests. We're always welcoming contributors. So please don't hesitate. But even if you don't, I hope that the methods, and I hope that the JavaFX code that we write to make that all happen, all the magic, I hope that you can take something from a value from it and even build your own tools, because it's a good thing, and we need more tools like this and to deal with these sorts of analyses of the future.